Is this on? Can y'all hear me in the back? Wonderful. Thank you very much, sir. My name is William Brett Johnson, and I go by my middle name, Brett. I apologize for the confusion. Like a responsible adult, I blame all my failings on my parents. That's their fault too. Today, I'm happy to share my work with Amos Winter at the Gear Lab on the effects of body segment inertial parameters on gait kinetics. And I'll be calling body segment inertial parameters BSIPs. And what I mean by that is basically the mass, center of mass position, and radius of gyration of different body segments, such as your thigh or your shank. One of the reasons we care about BSIPs over at Gear Lab is one of our missions is to create passive, low-cost, high-performance prostheses for emerging markets. And one of the strategies that we do to accomplish that is to optimize our prosthetic designs for a desired kinematic profile using a desired kinetic profile as inputs to a model of this prosthesis. The Indian population that we are targeting a foot for desires able-bodied kinematics. And previous work that we've done has shown that BSIPs affect the kinetic profile that would be required to create those target kinematics. In that previous work, grad students at Gear Lab, including Murthy, who's out in the crowd now, demonstrated that when you change a BSIP, such as the mass of the thigh, and you make it smaller, you're going to reduce the ground reaction force that's going to be acting on the body by reducing the change in linear momentum. And so you need to account for that change in the ground reaction force in order to calculate the proper joint torques to guide your prosthetic foot design. Following a similar principle, if you change the center of mass location of the thigh segment, you're going to reduce the moment arm and change the acceleration of it, and that will also reduce the ground reaction force. Now this analysis focused mainly on linear momentum. One thing that it did not look at or examine was how BSIPs affect changes in angular momentum. And that can have consequences on the torque that acts on the body during single support and double support, but we're focusing on single support. And also it can affect COP, which is the moment arm of the torque that's acting on the body. So our main question was then, how do BSIPs affect COP progression along the foot? Because it can have pretty big consequences on the joint torques. And so we went about investigating this with a computer simulation where I used kinematic data from a public database from HUMOD to animate a link segment model. I got some body segment inertial parameters from a set of regression equations, and I used that as a baseline condition. And then I varied the position and the mass of those position and mass of those centers of mass on those segments individually over a range of 50% to 150% to see how it affected the center of the progression of the COP under the foot. Now, this next slide is ugly. Please don't check out. I'll walk you through it. Again, I blame my parents. So the way that we calculated the changes in kinetics, particularly ground reaction force magnitude and COP progression, is first we started out with the force from the plate, which we're using as a proxy for the sum of the linear momentum of the entire body. And from there, when we add or subtract the mass, that is going to add or subtract a contribution to that net change in linear momentum. Thank you very much, Doctor. Now if I can only figure, oh, wonderful. So F plate, this is the proxy of the baseline condition, sum of total linear momentum. These terms right here, if I add or subtract mass to a segment, these add or subtract linear momentum to the system, and then I get a new estimate, F hat, of the GRF force. This next equation follows a very similar principle, but we're applying it for angular momentum. So we use the COP cross plate to get a torque a baseline torque acting on the whole body, and these terms here determine the contribution of changes in mass to changes in angular momentum. Then we take that torque, and we take that ground reaction force, and we use a pseudo inverse cross product to calculate the COP progression in the 4-AF position. And we made it through. Thank you for your patience. Let's look at something prettier. This is a plot of the COP progression under the affected side. This is the side where we change the mass parameters. And as we see, this is time and percent single support phase. This is CO progression in the 4-AF direction. As we go from heavier to lighter, the slope increases, meaning that the COP is progressing faster under the foot when we change the mass, when we decrease the mass. Likewise, we find the same trend when we decrease or when we move the COM of the thigh more proximally. And we also found out that if we observe the contralateral side, the unaffected side, it had the opposite effect. If we lighten the mass on the opposite thigh, it caused the COP to slow down under the foot. And same with the COM.
All right, I want to make sure we have some time for a question.
And I appreciate
Let's
that.
thank our speaker. If you want to come up and put your presentation. Do we have a question for William? Go ahead.
We just hand it off to whoever's talking. Or,
So was your assumption that the kinematics of the gait remains the same when you change the?
Yes. For this simulation, the target kinematics are constant throughout. And it's because the people we're designing the foot for want able-bodied kinematics.
I mean, if you change the dynamic parameter like mass, don't you think kinematic would change also?
I think it's possible. I definitely think that's possible. But I also think that there are main degrees of freedom to control so that people can go back to recreate able-bodied kinematics using different
So you want to force them back to able-bodied kinematics?
We're not saying, we're not trying to force them. We think they prefer it that way.
Okay, gotcha. Thanks.
What would you like the center of pressure to do?
That's a fine question. I'm really just interested in making sure that it isn't introducing an error term into our models. So I wanted to make sure that we were capturing all the behavior that we could expect from an expected torque profile so that we can get the right target knee torques and things like that from our devices.
All right, thank you.
Thank you.